So part 2, halogen alkanes react with ammonia to form amines. Just don't want to. So two conditions necessary for halogen alkane to react with ammonia to form amines. You want a warm halogen alkane with excess ethanolic ammonia. So the ammonia NH3 with lone pair of electrons attacks partially positive carbon, CBr bond breaks. That makes complete sense. In this case, however, we need these excess ethanolic ammonia dissolved in ethanol. Then you form this, where the nitrogen positive, the NH3, Br minus with lone pair of electron. That's nucleophilic substitution. Very easy. The ammonia swaps place with the halogen. And the halogen is obviously Br, the bromo. So in this case, then what happens is there's another lone pair of electrons under NH3, ammonia. And this acts as a base. It takes a proton, and this NH2 transfers electrons to the nitrogen, and this NH bond breaks as well. And this bit is reversible. You form this with the nitrogen with lone pair of electrons and an ammonium ion, an amide and an ammonium ion, amine and ammonium ion. And the ammonia removes a hydrogen from NH3, forming an NH4 plus ion. And the equation for halogen alkanes react with ammonia from amines, CH3 CH2Br plus 2 NH3 using 2 ammonia, that's stage 1, stage 2, with ethanol, obviously dissolving ethanol, warm halogen alkane with excess ethanolic ammonia, not just normal ammonia, ethanolic ammonia, to form CH3 CH2 NH2 plus NH4Br. And this Br minus with lone pair of electrons will eventually bond with this NH4 plus to form NH4Br. The ammonium ion reacts with bromine ion to form ammonium bromide. There you go, NH4Br. Halogen alkanes undergo elimination reactions. Now, when halogen alkanes undergo elimination reaction, this is in anhydrous conditions, aka without water. So state 3 conditions for halogen alkanes to undergo elimination reactions. We want a warmer halogen alkane dissolved in ethanol, and we want a warmer halogen alkane with the hydroxide ions. So the lone pair of electrons OH minus acts as base, takes a proton, left carbon now is a spare electron, so it wants to form a double bond. In order to form the double bond, the CBr bond must break, and that is exactly what happens. And then you form this double bond here, and what I would look at is this OH minus is bonded with here, so this hydrogen is going to be removed, so you're going to have a water molecule, and this Br is removed with the Br minus lone pair of electrons. So to draw this bit, which is probably the hardest step, obviously you're going to have a double bond here. You've got HH, HH, this Br's gone, you still got this hydrogen, so this hydrogen's here, and then you've got this CH3, which is there. And then see the overall equation, CH3, CHBr, CH3 plus KOH, the OH minus ions from potassium hydroxide, ethanol and relux to form CH2, CH3 plus H2O plus potassium bromide, KBr, because the potassium K plus will bond with the Br minus with lone pair of electrons. Bromine is added across a carbon-carbon double bond to form a colourless dibromo alkane. Bromine is added across a carbon-carbon double bond to form a colourless dibromo alkane. Now this is an example of electrophilic addition, is how bromine is added across carbon-carbon double bond forming colourless dibromo alkane. Electrophilic addition. H2C double bond CH2 plus Br2 CH2 Br CH2 Br. So you have got ethene, and what happens is it goes from the bond C double bond C to the bromine, partially positive, and it transfers the electrons to this Br minus, and this BBr bond, a Br2 bond breaks. So now you've got this carbon positive, bromine minus charge, lone pair of electrons bonds to it, and you form this 1,2 dibromo ethane. Now in this example, you can notice that ethene is completely symmetrical. You've got CH2 here, carbon-carbon double bond. And in this case, you only form one product, 1,2 dibromo ethane, because it's completely symmetrical alkene. However, if it's unsymmetrical alkene, will form a mixture of products, and then carbocation, a knowledge of carbocation will come into place. 10. Alkenes undergo electrophilic addition with hydrogen halides to form halogenoalkanes. Alkenes undergo electrophilic addition with hydrogen halides to form halogenoalkanes. Ethene plus HBr to form bromoethane. C2H4 plus HBr, C2H5Br, ethene plus hydrogen bromide, which is an example of a hydrogen halide, to form bromoethane, ethane, a halogenoalkane. How hydrogen bromide reacts with propene. And now you can notice in this case, propene is an unsymmetrical alkene, HH, and then you've got a CH3HH, so it's unsymmetrical. In this case, from the double bond to the hydrogen, H plus, HBr, from the middle of the HBr bond to the Br. You form this lone pair of electrons, Br minus, bonds to this carbon positively charged to form one bromopropane, which is the minor product. Then what happens, the same thing happens, but then the lone pair of electrons, Br minus, can bond here to form 2-bromopropane, which is a major product. So you can form two products, a mixture of products, the minor product and the major product. Alkenes will react with cold concentrated sulfuric acid to form alkyl hydrogen sulfates. Alkenes will react with cold concentrated sulfuric acid to form alkyl hydrogen sulfates. Two conditions to convert alkyl hydrogen sulfates into alcohols: adding water and warming in the reaction mixture. So cold concentrated sulfuric acid reacts with alkene, forming ethyl hydrogen sulfate in electrophilic addition. Ethene plus H2SO4, ethyl hydrogen sulfate. Alkyl ethyl hydrogen sulfate, which is an example of alkyl hydrogen sulfate. Then the alkyl hydrogen sulfate, in this case ethyl hydrogen sulfate, adding water plus H2O, warm the reaction mixture, should probably say warm or heat here, to form ethanol, an alcohol, plus the sulfuric acid H2SO4. Add cold water and warm the product. And what we notice is that the H2SO4 is regenerated by the end of the reaction. It's not used up. Sulfuric acid is not used up. Therefore, sulfuric acid is considered a catalyst, as the sulfuric acid is not used up. And the two conditions, adding cold water and warming the product, do what is called hydrolysis. Example of hydrolysis reaction, where it hydrolyzes to form an alcohol and sulfuric acid. So here's the mechanism. Ethene, from double bond to the hydrogen, positive, HO, from middle of the HO to the oxygen, partially negative. Oxygen now is minus charge, lone pair of electrons, bonds to the carbon which positive charge to form this ethyl hydrogen sulfate. So pretty simple. Then we want to add cold water and warm the product, and then we form ethanol plus the sulfuric acid with no charges. An overall reaction, H2C double bond CH2, ethene plus H2O, a cold concentrated sulfuric acid, which is a catalyst, to form ethanol, C2H5OH, which is considered a catalyst. Draw out the mechanism for elimination of water from methanol. So you've got oxygen lone pair of electrons bonds to a H plus. It's because it's done an acid catalyst. Now you've got this oxygen positive, and this carbon is now feeding the electrons toward the oxygen charge. This is showing the copper cation. The alkyl group is going towards positive charge, but that's not really necessary in the AQA mark scheme. But what is necessary, from the CO bond to the oxygen, so this leaves, and now, so from the lone pair of electrons and oxygen to this H plus, and then now the oxygen is positive, H2O leaves, so from middle of CO to the oxygen, and now the carbon is positive, and you've got H2O, and now the carbon is positive, wants to form a double bond, so it forms a double bond, C double bond CH. So this a H plus is lost, and now you've got ethene plus H2O plus H plus, and this is the mechanism for elimination of water from ethanol. And then this mechanism, the industrial method for producing alcohols, hydrating alkene using steam in presence of an acid catalyst, and the equation for production of alcohols, CnH2n plus H2O, reversible reaction with H plus to form CnH2n plus 1 OH. General mechanism for hydrating alkenes using steam in presence of an acid catalyst. So carbon double bond HHH, from double bond to the H plus, you form this. Carbon's positive. Now the lone pair of electrons in the H2O attacks the carbon, which is positive. Now you get this. Oxygen is positive, and now this OH, this H plus is going to leave. So from the middle of the OH to the oxygen, it leaves. You form ethanol plus your H plus. And these two mechanisms are very easy to confuse. I confuse them all the time. And, you know, obviously you don't really need to worry about, you do need to worry about it, but just keep going through it and you cement it in your mind and you won't be confusing them anytime soon. And that is the end of this video.